Welcome to lecture 32 of the course Marine Propulsion. The topic today is ducted propellers. The key concepts covered in today's lecture will be ducted propellers in general and the momentum theory for ducted propellers. So, here we will use the axial momentum theory to define the efficiency of a ducted propeller system. A ducted propeller is a screw propeller surrounded by a non-rotating duct. So, here we have a screw propeller which is surrounded by an axisymmetric duct which is in the shape of a shroud or nozzle, and the duct along with the propeller here forms the propulsion system. So, we have the propeller assembly as the propeller and the duct around it. If we look at the section, this part is the duct and this is the propeller. And these ducted propellers are typically used for vessels with very high propeller loadings where the duct also provides thrust along with the propeller. So, the initial concept for ducted propellers were developed as early as 1930s by Stipa and Cort, and that is why ducted propellers, especially the accelerated ones, are also called Cort nozzles. Here we have two views of the ducted propeller, one from the side and the second view here from the front, and here we can see that there is a small clearance between the propeller blade tip and the duct, and in ducted propeller the vortices generated by the propeller blade tip are suppressed by the presence of the duct, and both the propeller and duct generates thrust which is important for operation and thrust generation at high propeller loadings, that means low advance coefficients. There are two main design concepts for ducted propellers. The first one, which is most popularly used, is the accelerating duct, which are also called Cort nozzles. Now, these ducts increase the inflow into the propeller. So, they accelerate the flow into the propeller, and in doing so, the ducts generate forces, a forward component of which is the thrust force, and in addition to the propeller force, they can provide high thrust at high propeller loading conditions. Hence, they are used for vessels like tugs, trawlers and other vessels which operate at high propeller loading, so that the high thrust requirement can be met. On the other hand, we have another design concept called the decelerating duct, which reduces the velocity of flow into the propeller. These are specifically used for vessels where cavitation is a problem, and to mitigate the cavitation effects, the velocity into the propeller can be reduced using a decelerating duct. So, when we refer to ducted propellers in general, the usual reference is to accelerating ducts, which produce high thrust at high propeller loading conditions. Now, we will use simple axial momentum theory to evaluate the thrust and efficiency for a ducted propeller. Here we have the ducted propeller instead of the conventional propeller in the same axial momentum theory. So, the duct is shown here, which is an accelerating duct because it should accelerate the inflow into the propeller. We have the propeller which is taken as a momentum disk, and the same assumptions that we have used in the axial momentum theory will hold. V is the inflow into the domain. This is a section taken far ahead. And P0 is the pressure here. and we take another section far astern behind the disc. Here we have the total velocity v plus ua, where ua is the axial induced velocity, and the velocity through the disc is vp. And if we take a section just in front and just behind the disc, we have a pressure P1 here and P2, and because there is a pressure jump through the system, a net thrust is applied by the disc, and we have ideal flow assumption with no drag. So, the fluid column is flowing through the ducted propeller of a cross section area, let us say AP, and hence the mass of fluid column which is flowing per unit time, mass of fluid per unit time is m rho AP into Vp. This is the same as we have seen for the conventional propeller. Okay. Now let us apply Bernoulli's equation between the sections 1 and 2 ahead of the disc. That means in front. Here we can write P0 plus half rho v square equal to P1 plus half rho Vp square, right? And similarly, we can apply Bernoulli's equation between the two sections at 3 and 4 locations behind the disc, and then we will have P2 plus half rho Vp square equals P0 plus half rho. Total velocity far astern is V plus ua whole square. So, the first equation can be written as P1 plus half rho Vp square equals P0 plus half rho V square, just by interchanging the sides. This is 1 and this is 2. So, by 2 minus 1 we will have P2 minus P1, half rho Vp square and P0 will cancel out. This is half rho V plus ua whole square minus V square, and this difference in pressure between the two sides of the disc is the delta P, which is the pressure jump across the disc. So, this is pressure jump across the disc. This is given by half rho 2 V ua plus ua square. Now, what is the thrust that is generated by the propeller? The thrust generated by the propeller only is Tp. Here we have to remember that we have two thrust components, one from the propeller and one from the duct. So, the thrust generated by the propeller will be given by this pressure jump into the area of the propeller disc AP, which is mentioned here in this simple axial momentum theory. So, Tp is del P into AP, right. So, the right hand side we can write as half rho into AP, taking 2 UA common, V plus UA by 2, and then the thrust TP becomes rho AP UA multiplied by V plus UA by 2. So, this is the thrust which is generated by the propeller. Here we have to understand that the duct, being considered as an accelerating duct, should accelerate the flow through the propeller. So, the velocity of flow through the propeller disc Vp is V plus UA by 2, which is half the axial induced velocity. This part is same as the conventional propeller without the duct, plus the additional velocity which comes due to the flow acceleration by the duct. Let us take it as UD. Now, if we go back, what is the momentum of the fluid in the inlet? The velocity was V, and far astern behind the disc the velocity is V plus UA. So, the total thrust applied by the propeller and the duct together is the change of momentum of the fluid that is passing through this ducted propeller system between the section at 4 and 1 in unit time. So, if m is the mass of fluid per unit time, which is shown here, the change in momentum which gives the thrust force can be calculated as m V plus UA minus mv. Now, this is the total thrust TO, which is basically TP plus TD, where TP is the thrust component of the propeller, which is already shown, and TD is the thrust component of the duct. So, this is the total thrust from the change in momentum. Now, TO should be equal to rho AP into Vp, which is the mass that has been shown in the earlier slide, into V plus UA minus V is UA. Now, if we substitute the value of Vp, V plus UA by 2 plus UD, which is the effect of the duct into UA. This is the total thrust of the duct plus the propeller. Now, the ducted propeller is considered as a single propulsion unit, which includes the performance of the duct as well as the propeller. So, when we calculate the ideal efficiency of this system eta I, it should be the total thrust TO multiplied by the velocity head against which the thrust is being provided, which is V as before, divided by the input power. So, T multiplied by V is the power output from the system. Here we also have the duct along with the propeller, that is why instead of Tp we have used To, which is the total thrust, and the input power is given from the change of kinetic energy between the section far astern and the inlet as before. Now, if we substitute the values of T and M, we can write eta I as rho AP UA into V plus UA by 2 plus UD into V by half mass, which is AP multiplied by the velocity through the propeller disc V plus UA by 2 plus UD into V plus UA whole square minus V square, which is 2 V UA plus UA square. There are certain terms which will be cancelling out in the numerator and denominator. Rho AP. So, this is V UA into 2 by, if we take 2 UA common, V plus UA by 2, right. Now, this can be written as V by V plus UA by 2, and in the same way as before, we will non-dimensionalize both the numerator and denominator dividing by V. So, this becomes 1 by 1 plus UA by 2V. So, this is the same equation that we have obtained as before. Now, for a ducted propeller, we have the propeller thrust, which is Tp, and the total thrust To from the duct and propeller combined, and we will define a factor tau, which is the ratio of the thrust generated by the propeller to the total thrust from the ducted propeller system. So, if we use the expressions for Tp and To, this is rho AP the total velocity through the disc into UA. So, this becomes V plus UA by 2 by V plus UA by 2 plus UD. Again, if we divide by V and make it non-dimensional, this is 1 plus UA by 2V by 1 plus 2V plus UD by. This is tau, which is the ratio of the propeller thrust to the total thrust from the ducted propeller system. Now, if we define the thrust loading coefficient, which is based on the total thrust. So, this is the thrust loading coefficient based on the total thrust, that is TO by half rho AP V square. The denominator is same as before. So, we can write rho AP V plus UA by 2 plus UD into UA by half rho AP V square. We will see that it comes to 2 1 plus UA by 2V plus UD by V multiplied by UA by V, because rho AP will cancel out and this V square we have used to non-dimensionalize both the term within the bracket and also the UA outside. Now, if we compare this thrust loading coefficient here with the value of tau obtained, this particular expression, we can write it as 2 by tau 1 plus UA by 2V into UA by V, where tau is given by this particular expression. Okay. The reason of doing this comparison is to get an expression of CTL, the thrust loading, based on the ratio of thrust for the propeller and the total thrust, which is given by tau. Now, as a final expression, we will relate the thrust loading coefficient of this ducted propeller unit to the ideal efficiency that is obtained in equation 6. So, this is 7. We will use this relation 7 to get the relation between CTL and eta I. Let us, for simplicity, assume UA by V equal to x. Then from 7 we can write CTL is 2 by tau 1 plus x by 2 into x, which gives the equation tau CTL equals 2x plus x square, and finally we have the quadratic equation x square plus 2x minus tau CTL equals 0. And from this equation we can simply calculate x as minus 2 plus root over 4 plus 4 tau CTL by 2. Only the positive root is taken because UA by x must be positive. The axial induced velocity divided by the inflow velocity, this non-dimensional fraction should be positive. So, x is UA by V equals root over 1 plus tau CTL minus 1. So, we can replace this particular value of UA by V in the equation for eta I. eta I will now become 1 by 1 plus UA by 2V. That means this UA by V divided by 2 root over 1 plus tau CTL minus 1 divided by 2. So, finally, we have the ideal efficiency is given by 2 by 1 plus root over 1 plus tau CTL. This gives the final relation between the ideal efficiency and the thrust loading coefficient for a ducted propeller. Now, if we compare this expression to that of a conventional propeller where there was no duct, the tau term was not there. Now, tau is defined by Tp by To. When there is no duct for a conventional propeller, so conventional propeller no duct, then there is no thrust generated by the duct, then To equal to Tp. The thrust produced by the propeller is itself equal to the total thrust, that means tau equal to 1. So, in this particular expression, if we put tau equal to 1, we will get eta I is 2 by 1 plus root over 1 plus CTL, which is the same expression that we have obtained for a conventional open propeller without the duct. Okay. So, this expression of ideal efficiency for a ducted propeller gives the relation between the thrust ratio of the propeller to the total thrust tau to the ideal efficiency of the ducted propeller system using momentum theory. This will be all for today's lecture. Thank you.